We present in this segment a general framework for solving estimation problems, like the recovery problems we are addressing during this and next week. The framework is rather intuitive and quite powerful, and it has been applied towards the solution of various signal estimation problems. Of course, we apply it here specifically to the image restoration problem. According to it, we are interested in estimating a signal that belongs to a number of sets of signals. Each set represents the collection of signals that possess a certain property. For example, we can define the set of all smooth images, or the set of all images that only accept non-negative intensity values, which is a very reasonable request given the nature of light. If the sets are convex, then the problem we are asked to solve is simpler. One way to obtain a solution in the intersection of the sets, assuming it is not empty, is to alternate orthogonal projections onto these sets. It's a rather intuitive and smart framework, as we will see. I would like to briefly discuss another approach towards solving recovery problems or estimating a signal under the name of set-theoretic approach. And we'll see that if we apply it to the specific problem at hand, the image restoration problem, we can come up with another version of the constraint least squares filter. This approach is rather intuitive. According to it, we are looking for a signal, an image, that has a set of properties. So each property defines a set, such as the one shown here. So all the signals, all the images that belong to this set have a specific property. The set of signals that have the second property we are interested in define another set, such as this one, and there could be a third, a fourth property, and so on. So for the problem at hand, the image restoration problem, the example of the first set is a set of signals that satisfy this inequality here. So this is the set of images that have high frequencies, that have energy at the high frequencies less than epsilon squared. C is again a high-pass filter, and therefore this is the energy at high frequencies. And this is the smoothness constraint, as we explained earlier. So all these signals that belong to this set are smooth. By the way, this set is shown as an ellipse here in the n-dimensional space, is an ellipsoid, the generalization of an ellipse, and is therefore a convex set, an important property of such set. The second set we can define based on our restoration problem is shown here. So it's the set of images that have this difference, y minus hf, being less than e squared. And this is the fidelity to the data constraint. So we are looking for an image that has both of these properties. It's smooth and satisfies the fidelity to the data. Therefore, we're looking for an image that belongs to the intersection of these two convex sets, and this intersection is going to be convex as well, since the sets are convex. So this is the general setup of a set-theoretic approach. And the question now is, how can one obtain a solution in the intersection of these two sets? By the way, these two sets may have a non-empty intersection or may not. So typically, after we find the solution, we do a posterior test, and we test if indeed the solution satisfies both constraints, belongs to both sets, as we would be interested in. So one approach to find a solution is to bound the intersection by another ellipsoid, as shown here, and choose the center of this ellipsoid, of this bounding ellipsoid, as the solution. We'll see that this approach can result in a constraint least squares filter. So I have again two sets, a set C1 and C2. Each of them represents a set of images with desirable properties. They intersect. C0 is the intersection of the two sets, and I'm interested in finding a solution in the intersection of the two sets. An intuitively very clear approach is to utilize projections onto convex sets approach or algorithm. So according to it, I start from an arbitrary initial condition F0, and I project image F0 onto the first set. So this is the projection P1 on set C1 of F0. Then I take this point and project it onto the second set. So this is now the projection 2 onto set 2 onto set C2 of the point P1 F0. And I call this F1. And I keep repeating this process. I now take this point, project it to C1, and then I'll take it and project it back to C2, and so on. So the theory tells us that in general, if I have M such convex sets, if I repeat this projection onto convex sets or alternating projection algorithm, right? I start with an F0 arbitrary and project onto the first, the second, the M set. This gives me the new update. F of k minus 1 becomes f of k, and I keep repeating this way. Then in the limit, after so many iterations, the solution F star here is going to be in the intersection C0 of these M in general convex sets. So this should be a very, again, intuitively clear algorithm. Of course, these projections, depending on the description of these sets, might be a rather straightforward way to find these projections, or it might be terribly complicated. So the theory of set theoretic estimation, following then any of the two solution approaches I mentioned, has been applied to a number of problems successfully. And if I apply it now to the restoration problem at hand, we'll see what expressions we obtain. So for the image restoration problem, we're looking for an image that belongs to both of these sets. This is the set that represents the fidelity to the data, and this is the set that represents the smoothness constraint. So according to the first approach we discussed, we'll find an ellipsoid bounding the intersection of these two sets, and then it can be shown that the center of this ellipsoid, of this bounding ellipsoid, is given by this expression. So this is the expression for the constrained least squares filter that we derived earlier. The difference being that now the regularization parameter alpha is given to us because we assume that we know these two bounds, E and epsilon. It should be clear that by picking E and epsilon a certain way, these two sets may not intersect if they both are, for example, chosen to be very small. And therefore, I need to check if indeed this solution I find, it belongs to both of these sets that it should belong. The second approach we discussed is the projection onto convex sets. So if I follow this, I have two sets. The first one is set 1. So this is C1, this is C2. And this is the projection of f of an image onto the first set P1 is given by this expression. And lambda here needs to be chosen appropriately so that P1f belongs to set C1, or in other words, P1f satisfies this first expression. This is the projection onto the second set, the set of smooth images, and similarly lambda 2 needs to be chosen appropriately so that P2f belongs to the second set. So keep alternating the projection, so to these two sets I'm going to converge to a point in their intersection. So again, this is a specific application of this set theoretic approach to the image restoration problem. However, now that hopefully you do have a grasp of the basic idea, you can search and see that this approach, estimation approach, has been applied towards the solution of additional problems of interest.